So we talked about an example in the last video about how motion, the changing of the area of a loop, can induce current in that loop. And then specifically this chapter looks at that quantitatively, looks at it in more detail. That's called motional EMF. They use a motion to generate a current. So again, motion is one of the leading causes of induction in most electric motors and electric generators. Motion is used to generate current in electric generators. So we have the same setup, or a very similar setup to what we had in the previous video. We have parallel rails connected at one end by now I've placed in your book places an explicit resistor there, so you can calculate what the current is if you know what the resistance value is in the circuit, and you know the EMF in the circuit. I have a blue rail here that can slide back and forth. Your book moves it to the left some distance delta x. So it is here, it slides to the left. The entire rail itself, the two large rails are separated by some distance L. So looking at Faraday's law, the EMF that's generated, and your book just uses the symbols EMF. Again, I use this curly E to represent EMF. It's the same thing. The EMF is equal to the negative times the number of loops times the change in magnetic flux with time. I'm just going to look at the absolute value of the EMF. I'll use Lenz's law to figure out the direction. So I'm just looking at the absolute value of the EMF. How many volts is going to be generated? Depends on the number of loops times the change in magnetic flux with time. Well, there's only one loop here, one loop of wire. I don't have hundreds and hundreds of loops of wire here. So N in this example is equal to 1. A single loop of wire, so N just drops out of the equation because it's equal to 1, doesn't change anything. I want to look at the changing magnetic flux now, because that's the only thing that's left in this equation. How does the magnetic flux change with time? Magnetic flux is made up of three things, right? The magnetic field strength, the area the magnetic field is going through, and the angle between those two vectors. Is the magnetic field going perpendicular to some area, or is it, should I parallel the surface coming out here, the vector is parallel to some area, or is it perpendicular? Well, here the magnetic field is going into the board. The area, the plane of the area is perpendicular, but again, the surface we measure from the normal, which is sticking out in this case. Imagine the area like this, sticking into the board. So the angle between the magnetic field strength and the area is maximum. Angle is 0 degrees, cosine of 0 degrees is 1, so the angle falls out of this equation. This is set up to have the maximum flux in terms of at least the angle. Right? Any other orientation, and I reduce the amount of magnetic field lines that will be going into this area. So now the magnetic flux, the change of magnetic flux, just depends on the magnetic field strength in the area. The magnetic field, the red X's, they don't change. Right? The magnetic field is how strong the magnetic field is. We're assuming the magnetic field is constant throughout this entire area, and it doesn't get weaker or stronger with time. It's just present. So the magnetic field doesn't change with time. I'm going to pull that out here. What does change with time is the area. As I pull this to the left, the area gets smaller. How much smaller? Well, that's delta A, the change in area. That's this rectangle shown here with a green insert. Well, that area is just the length times the width. The length is how far the rails are separated. The width, delta x, is just how much did I move it. If I didn't move it at all, delta x is 0, and there is no change in area. The bigger delta x is, the bigger delta A will be. So the changing flux is the magnetic field times the change in area. Again, the magnetic field isn't changing. What is the change in area? Well, it's the length times the width. So I replace delta A here with the length times the width. The length doesn't change with time, right? These rails stay the same distance apart. What does change with time is this position. So when I plug this delta flux back into the equation here, divided by delta t, so the flux is delta psi over b divided by delta t, I get B times L times delta X over delta T, where B is the magnetic field strength, L is the separation of the rails, and this is the change in position with time, horizontal position with time. Well, way back in first semester, we talked about kinematics. We talked about how objects change position with time, and we have a word for that, right? That's velocity. Changing an object's displacement with time is velocity. So, or in this case, speed, if you will, is the magnitude of the velocity. So the EMF that's generated depends upon the magnetic field strength. It depends on the length or the separation of the two rails, and it depends on the velocity of this blue rail, the bar attaching the two rails, so the rail bar. So if you want to generate a strong EMF, a strong voltage in the circuit, you need a strong magnetic field, you need the bars separated by a large distance, and you need to move the blue bar or the rail bar rapidly. If you don't move the blue bar, the area doesn't change. If the area doesn't change, the flux doesn't change. If the flux doesn't change, no current is generated. So here's an equation for this system, this motional EMF. The motional EMF is equal to the magnetic field. So no magnetic field, no magnetic flux. So if the magnetic field is zero, there's no EMF generated. The separation here, length, right? That's related to the area change. If the two rails have a smaller area, then there's a smaller change in magnetic flux, which means smaller EMF. And how fast you move this rail back and forth. And that was demonstrated in the first video at the end, or was it the second video at the end, where I demonstrated, first video, in this section where I demonstrated moving a magnet back and forth rapidly. The faster you move it, the bigger the current that's drawn, the bigger the galvanometer needle moves because you're generating a more powerful EMF. So if you know what the EMF is, and you know what the resistance in the circuit is, you can calculate the current of the circuit. So here's the equation for the current in this circuit. The direction is given by Lenz's law. And again, Lenz's law tries to, let's use orange here to represent the current. Lenz's law tells you that the current will appear in such a direction to maintain the flux that was going through the circuit before the circuit started changing. Well, the magnetic field lines are going into the board here. When I pull this to the left, I'm decreasing the flux into the board. As I pull this to the left, fewer and fewer magnetic field lines will end up in this area here. So a current will develop that will try to put magnetic field lines back in. Let's see if I get it right the first time this time. The current will be, in my guess, is clockwise. And we'll use the right-hand rule to verify this. Current will go clockwise around the circuit. So, fingers in the direction of the current. If this is the current, grab the wire. My fingers are going into the board, reinforcing the magnetic field that's weakening, or the magnetic flux that's shrinking as I pull this to the left. Again, current going to the left, thumb in the direction of the current, grab the circuit. On the top of the circuit here, my fingers go into the board, reinforcing the magnetic field, and so on. So this is the correct direction, clockwise, if I pull this bar to the left. If I pull the bar to the right, same equation still holds. It's the same equation, but the direction of the current flips, and it goes counterclockwise rather than clockwise.